Hello, I'm Paul Beckwith. I'm with the University of Ottawa Laboratory for Paleoclimatology and also with Carleton University, the Department of Geography and Environmental Studies. So just to remind you, we have our Earth here. Okay, let's put it the right way. There's North America. Okay, let's look at from the Arctic polar view. And let's put our rubber band around here, which represents the jet stream. Okay, so we've got the jet stream circumventing the planet. The circumference of the elastic band, we'll call it L, capital L. So we can make the analogy to the length of a violin or guitar string. So that's the separation between these two black lines. And this is the fundamental frequency. So the wavelength is actually going to equal 2L in this case. In this case, we can get a whole wavelength between here. That'll be the next frequency. This is the n equals 3 frequency. Notice these n's correspond to the number of nodes. So there's one node here, there's 2 nodes here, 3 nodes and 4 nodes and so on. For n nodes, the general case, we have the equation n times the wavelength is equal to 2L. The vibration always has to be fixed at the end points. The same as on the Earth, we can have that fixed point is the same, and we go all the way around to the fixed point again for L. So the nth node, lambda n, equals 2 over n times L. Now, in the case of the Earth, what I've been saying is it's been determined that n equals 6, 7, and 8 lead to basically persistent waves or stuck waves, which then leads to extreme weather events. When n equals 6, so lambda will be 1/3 L. So we can get 3 whole wavelengths around the surface of the Earth. When n equals 7, we get 3.5 wavelengths. And when n equals 8, 2 over 8 is 1/4, so lambda is 1/4 L. That means we can get 4 complete wavelengths around the whole Earth. And when those conditions are satisfied, we get planetary resonance. And these waves get stuck, and we get these extreme weather events, like the 2010 heat wave over Russia, lasting 30 plus days. 30 to 35 degrees Celsius temperatures. They lost 40% of their grain crop. 2003 heat waves in Europe, killing 70,000 people plus. Same sort of thing. Drought in Texas, heat wave in Texas in 2011. The persistent drought in California that has been tampered or somewhat alleviated by the atmospheric rivers. And so on. So basically we get these planetary resonance. So we can make the analogy to electronic circuits, to optical waveguides. You get this sort of mode situation. In optical waveguides, then the depth direction will also affect it. So these are transverse electric modes. This is the n I've been talking about, the first number, 1, 2, 3, and the other number will be in another dimension. So we can actually make an analogy in a 3-dimensional analysis of the wave if we want, based, more analogous to the waveguide idea. So the other thing is that these wavelengths, every object, every material has a resonant frequency, if you like. Drive your car along the highway, you might hit a speed where you get a lot of vibration, and then you go a bit faster or slower, that vibration goes away. That will be a resonance. In the case of when you hit the resonance frequency of when long wave radiation coming up, or heat coming up from the Earth, it reaches the resonant frequency of the greenhouse gases, the CO2, the methane, the nitrous oxide. It causes those molecules to vibrate faster, and therefore they absorb the energy, trap the heat, and warm the planet. The Tacoma Narrows Bridge in Washington in 1940 shook itself apart because the breeze was blowing on the bridge, and it reached a resonance frequency. The amplitudes went up, and then the bridge basically broke apart. So here's the type of frequencies. There was a twisting frequency. There was a wave frequency along this axis. And the bridge basically, the frequencies, the magnitude of the oscillation got amplified until the bridge just basically broke apart and collapsed. Okay, so now let's go back to the atmosphere. So we're getting this, so here we have our, the rubber band around the planet, and this is in normal situation. There's not a lot of variation. This is at the surface, and this is what we have now, or in 2013, where the winds on the surface are going, the red is southward, the blues are northward, and you can count 1, 2, 3, 4, 5, 6, 7, 8. So n equals 8, and we get this resonance. So n equals 6, 7, or 8, we can get this sort of pattern, and we get the extreme weather event. So let's have a look on Earth Null School, and this is what we have. This is what we have right now. So this is basically a couple meters above the surface, and you can see these wind patterns. So basically, what the study is showing is that there's more north-south movement. So there'll be southward movement here, northward movement here, southward movement in another place, northward, and we're getting each of these particular situations is a node, and if you get 6, 7, or 8 around the planet, you get a resonance, and you get this amplification. The wave amplitude gets bigger, and then you get, when the pattern gets stuck with 6, 7, or 8, then you get the extreme weather events. So this is at the surface. If we look at the jet streams, look at high altitude, then this is the sort of thing that we get. Now you'll notice as I look at this particular point over here, so if you go down, so this motion here at the surface is actually, air is dragged. Basically, the jet streams are pulling air along beneath, and we get this type of dynamic effect. So this is the high altitude winds, and we get very broken, very fractured jet streams, which I've been talking about and other people for 4 or 5 years. So the thing about this study that has just come out is it's looking at the surface winds, and it's looking at a lot of data, temperature data, wind data at the surface, and it's also running the state-of-the-art models to look at why, what sort of conditions are required to get this resonance, to get this stuck pattern. So let's go to Climate Reanalyzer, and let's look at the surface winds here. If it'll bring it up. Okay, so this, you can see this type of feature that we saw in Earth Null School, and you can see it's not just in the northern hemisphere, but it's actually getting, we're seeing lots of variation also in the southern hemisphere, with these jet stream behaviors, these whirls, and so on. So this is, the study by Mann et al. That was just done is in the northern hemisphere. So the jet stream winds, you can see they're very, very streaky here. And we can go, so they're very streaky. These are areas of high winds and then lower winds and high winds. So they're very fractured and streaky and, very wavy as well. So let's have a look, go to the northern hemisphere, and you get this sort of thing, these strong waves. Okay, so, and of course, in the crest of a wave, you get positive temperature anomalies. Let's go back here. Okay, so you can look at the temperature chart. You can see these very strong anomalies. So this will be, this would be in, a wave would be coming down this way, and, would be coming down this way and be broken up and so on. Northern hemisphere, you can see this incursion. This would be the trough of a jet stream, etc. Very high temperatures here. Sea surface temperatures, anomalies are also you know, very, you know, they're affecting, you know, they're affecting weather around the planet in strange ways. We've got a very warm Gulf of Mexico, very warm Gulf Stream coming up here, and we're getting to back to here. This is so the South America. We're getting a very warm ocean temperatures here. It looks like it looks like we're building up into another possibly another powerful El Nino event, following on the tails of the record largest El Nino event. So let's have a look at some of the details of this paper then. Okay, so this is the paper that just came out recently. So the influence of anthropogenic climate change on the planetary wave resonance and extreme weather events. Okay, so these persistent episodes of extreme weather are associated with these quasi-stationary atmospheric Rossby waves, if you like. Zonal wave number 6 to 8. That's the number N I was talking about. N lambda equals 2L, where L is the distance around the planet. Okay, so quasi-resonant, so we're getting amplification of these waves. They're traveling more northward, more southward, and as I demonstrated in a previous video, they've gone up to the North Pole. As northward as the North Pole, you can't go more north than that. And they've gone so far south that they cross the equator and go into the southern hemisphere. And that needs to obviously be studied a lot more. I did a video it's about 9 months ago now on that phenomena. Okay, so what we have is we have like a waveguide, if you like, in the atmosphere, and we get the amplification. We get these resonant frequencies when the waves are set up and they get stuck. Now there's a lot of other factors that come into play, like there's the topography comes into play. If there's mountains, etc., then the waves will act as a block and the wave will go south or north of that. And if there's a lot of north-south mountain ranges, that can cause very large dips or troughs and crests in the wave. There's also temperature gradients between the land and ocean, and as the ocean temperature is warm and the land temperatures change, then that can also affect the behavior of the jet streams. So this paper does talk about the 2003 European heat wave, the Pakistan flood, Russian heat wave in 2010, the drought and in Texas and in California. So let's just have a look at some of the... So basically what this study showed is it looked at... Let's go down to the diagrams here. Okay, so what it did is it looked at the temperature data at the surface, and it looked at the from 3 different models, you know, over time, from the climate reanalysis data from 1979 to 2015, I think was the extent of the study. It also ran the models, ran the computer models, the state-of-the-art computer models, to try to see how they compared, what needed to be, what parameters were in the models when you had this resonance occurring. So this is the zonal temperature mean. So if you go around the whole planet at a given latitude and take the temperature, then the average, the climatology, the long-term average is the black line, and the quasi-resonant amplification conditions are the dashed line. Now if you take the difference between these two, okay, this is a typo. This should be in Kelvin, not degrees Celsius. Michael Mann can correct that. If you take the difference between these two curves, then you get this sort of thing. So when we get a large temperature anomaly, so as the north is warming, we get the Arctic temperature amplification. Some latitudes are warming faster than others. This is what the temperature profile. And then if you put that into the model, and you can talk about the quasi-resonant amplification fingerprint and the temperature gradient, and then you can actually do the simulations and stuff. And what we're finding is that in the last decade or so, this type of effect